Okay, folks, in those first two videos, we really did the heavy lifting for this section, where first we looked at a discrete case where we could actually compute the center of mass and formulaically by just taking the two masses, and we were able to say basically that the x-coordinate of the center of mass was this total moment divided by the total mass. That was all well and good, but it was for a discrete case, where in this case we just had two pointwise masses. So then we went ahead and sort of rebuilt the idea of center of mass, but in this case considering the object to be a continuous region rather than a collection of pointwise masses. And when we did that, we said, okay, well then the x-coordinate of the total of the center of mass is again the total moment divided by the total mass. That part looks exactly the same as we had here, but now we can compute the total moment through this calculation here and the total mass, as we've been doing actually for quite a while now, through this calculation here. The difference is now we've got this, so for this total moment, we think of weighing the mass at an individual point by how far it is from the origin, and that gives a notion of moment, which I like to think of as sort of being like torque. Okay, so all of that is summarized in this expression, in these expressions right here. In this class, we're going to use a lowercase m, in this section at least, when we're talking about mass. And notice that that calculation for mass should look the same as what we've been doing, where we say the mass is the integral evaluated from a to b of rho sub x dx. Notice that this is instantaneous density times a small unit of length. But in the 1D case, that's what we mean by volume in one dimension. And so we've got density times volume, and all of that together gives us a small unit of mass, and we add that up for all points along here. So this is again just recalling the formula that mass is equal to density times volume. Folks, one thing I forgot to say in the previous video, we're using the symbol rho here for density. There is no connection whatsoever between us using that symbol rho for density and us using the symbol rho for the radius when we're in spherical coordinates, which we've actually only just recently learned, and that could be a source of confusion here. So rho here is referring to density, and it is not referring to a spherical radius. Okay, all that together, we're now ready to tackle this problem, and I think that you're going to find that this part is going to be fairly straightforward. So the first question is, in A, we're asked to find the mass of the rod. Well, we know that the mass of any one-dimensional object, continuous one-dimensional object, will be the integral from its starting point to its ending point along the x-axis of its density times a small unit of length. That gives us a small unit of mass, pointwise mass, and we're going to add that up over the entire interval. Okay, so in our case, this would be the integral from 0 to 1. How do I know that? Because we're told that we're given a mass, a thin rod of length 1. And so we choose to place this rod on the x-axis, and we could put it kind of wherever we want, but let's go ahead and put it right here. There's 0, and this mass, this rod has a length of 1. So there it is. Now, the kicker here is, unlike, if this were of uniform density, by the way, just like the broom video that we saw, if this were, just like we saw somebody doing in the broom video, we're looking for a balance point. And if this were of uniform density, the balance point would be right in the center, meaning the center of mass would be exactly 0.5. But this is not, and that wouldn't be a very exciting problem, but this broom does not have uniform density. Instead, it is more dense towards the right endpoint. Its density is at 2 at the right endpoint, where it's only 1 at the left endpoint. So if you were to think about this as having, I'd like to draw these dots to represent particles, we are less dense here, and as we get closer to the right endpoint, we're more dense. Okay? All right. So all we need to do then is take the density, which we're told is 1 plus x cubed. That gives us the density at any point along this rod between 0 and 1, and we're going to evaluate that integral over the interval 0 to 1. So this would be x plus 1/4 x to the 4th, and we're evaluating that from x equals 0 to x equals 1, and that would give us 1 plus 1/4, and that comes out to be 5/4 is the mass of this. We'll just go ahead and assume, I didn't put units on here, we'll just go ahead and assume that we're in the SI system, so put 5/4 kilograms. Okay. So nothing new here in that we're just evaluating a simple ordinary integral, but we are interpreting that as the mass of this system. Now, what's a little bit more complicated is now we're asked to find what's called the total moment. And for total moment, we're using the capital letter M here. And the hard part to remember is that we're going to take again, a small amount of mass, which is our rho sub x dx, but now we want to, I think of it as weighing it or multiplying it by its lever arm. Weigh it by its lever arm, multiply it by its lever arm. So we've got this factor of x in here, which is very easy to forget as you're working these problems. Okay, so this will be the integral from 0 to 1 of x times 1 plus x cubed dx, which is equal to the integral from 0 to 1 of x times x plus x to the fourth dx, and we can evaluate that as 1/2 x squared plus 1/5 x to the fourth, evaluated between 0 and 1, and that gives us 1/2 plus 1/5, which would be 5/10 plus another 2/10, or 7/10 is this total moment. Now, really, the total moment for our class doesn't have a lot of meaning in its own right. It is one thing that we calculate in evaluating the center of mass. But it has to do with thinking about sort of this idea of at each point along this rod, we're going to compute the torque that's generated. So for example, this x-coordinate right here, we're going to be computing something like the torque based on that particle mass right there. And how that would be affecting that torque that would be generated on the origin, thinking of that as our fulcrum or whatever for the lever arm. Okay, what I'd like to do is before we finish out the calculation of computing the center of mass, I want you to take a look at this rod that I've drawn, and I've tried to represent its density with the orange dots above it, where the orange dots are more compact. That means the rod is more dense, and where they're more spread out, that means the rod is less dense. So if you wanted to think about this, maybe if this rod weren't infinitely thin, maybe you fill it first with some cotton balls, and then you fill it with some beans, and then you fill it with some rocks, and then you fill it with lead bearings or something like that. It has this variable density through it. Where would you expect the center of mass to lie on that? So I want you to decide approximately where you think that would be. Okay, hopefully you've taken a guess at this, but we now have a way of computing that center of mass by saying that our x bar is simply our total moment divided by the mass. And we found the total moment of this, just a moment ago, we found the total moment of this to be 7/10, and we're going to divide that by what we found the total mass to be, which was 5/4 of a kilogram. And if we simplify this, we end up with, let's see here, this would be 28/50, which reduces down to 14/25, and that's in x units, so that's meters. So we just found that our center of mass is right about, maybe right there. There's our x bar. It's not 12.5, so we're not right at the center. We're not right in between the two endpoints of this. Because of this non-uniform density of this rod, we are slightly to the right, and that should fit with your expectation. Okay, folks, that's all I have to teach you in this first pre-work video. What I'd like to do is show you where we're going. Okay? So in class tomorrow, we will be developing the integrals for computing the center of mass for a 2D and 3D object. I'll just say it now. In 2 dimensions, we're going to call a plate, which we could think of as being infinitely thin, but it's some plate that lives in the XY plane. We're going to call that a lamina. And we'll kind of explain that a little bit more in class. But if we want to find the center of mass of a lamina, or this 2D plate, we're going to use very similar formulas to what we saw before. And so you're going to go ahead and use these two formulas to compute the x-coordinate of your center of mass. That's the x bar, that's the x-coordinate of the center of mass, and your y bar, that's the y-coordinate of the center of mass. And there you can think of that as finding the balancing point. Okay. If you remember in one of those videos I had you look at where we had this, it wasn't quite actually a lamina, but we had this very thin bird that the physicist was looking at, this very thin bird that looked like this, and he found the balancing point to be right there. Although this bird is actually three-dimensional, you can sort of think of what he was doing is talking about the XY coordinates of the center of mass, which happen to be right at the beak of this bird, which is why you're able to balance it there. So what I'd like you to do is just go ahead and work through this problem where we've got a lamina D described by this region. So you're going to have to develop what that region looks like. And we've got a density it's not uniform throughout, meaning it weighs more in different locations in the XY plane, or it has a different, weighing is kind of the wrong word, it's more dense in different locations in the XY plane. And I want you to compute the center of mass using these equations up here. And if you get stuck, I've got a solution hyperlinked for you that you can take a look at. So that's the last thing I've got for this pre-work, and I will see you all in class where we will learn how to find centers of mass. We'll learn what these formulas mean, and we'll learn how to find the centers of mass of three-dimensional objects, and that's as far as we'll take this topic.